We talked about this. We talked about collections class, polymorphism, right. This is where we left off, right? Polymorphism. Now this is a concept that a lot of students, when they first, wait, I don't know if I'm recording. Give me a second. Oh, no, I am. Good. It's a lot of students feel as if like, oh, wait, what? This is weird, but you're thinking too hard. Just listen to what I'm saying. It probably is already kind of what you expect intuitively. Like, remember how I could make a stack reference variable, right? But I could either make a new array stack or a linked stack. But the reference variable is just of type stack. But the actual object that exists is of type array stack or linked stack. They're both stacks. But although the reference variable's type is stack, the actual more specific type that it's referencing could be different, like array stack, linked stack. And like, let's say I've got a reference variable referencing a stack, and I don't know if it's a linked stack or an array stack. And I ask you the question, okay, if I say like myStack.toString, which version of the toString is it going to run? Is it going to run the linked stack or the array stack version? It's kind of a trick question because the answer is, well, it depends. Is it an array stack or is it a linked stack? In the first example there, where I say myStack equals a new array stack, and then I say myStack.toString, it's going to go to the code in the array stack class and run that code to do the toString. But if I have myStack equals new linked stack, so it's referencing an actual linked stack, .toString, it's going to call the toString in the linked stack. And maybe using toString was a bad example, like enqueue or dequeue. When I say myStack.enqueue, which version is it going to run? Is it going to run the array stack version or the linked stack version? Well, that entirely depends on what the type of the object is. So the behavior of the object is dependent on what the type of the object actually is, not the reference variable. Okay? All right, yeah? So this is where like the idea of polymorphism comes in. Yeah, and be aware like you can't do this. Array stack, myStack equals a new linked stack. You can't do that because an array stack is not, or a linked stack is not an array stack. They're not the same. They're both stacks, but they're not actually the same. Now, they are both objects though, and you could do something like this if you wanted. Not just as an FYI. So like on line 2, so let's break this down. On line 1 of that code, myStack equals a new linked stack. What is the type of the reference variable myStack? This is a quiz for you. What's the type of the reference variable? Pardon? Nope. What's the type of the reference variable? It's just a stack. There's no trick here. It's just a stack. What is the type of the thing that the reference variable is referencing? Tell me. Yeah, there's no trick question here. You're looking at me like I'm trying to trick you. No. So the type of the reference variable is myStack, but the type of the thing that the reference variable is actually referencing is a linked stack. And now, what is the type of the reference variable O? Object. What is the type of the thing that the reference variable O is referencing? It's not a trick question. Pardon? No. A linked stack. Because remember, we're copying, it's a copy of the reference, not the actual, right? So we have two reference variables, myStack and O. the myStack reference variable is a stack type. The O reference variable is an object type. But the reference variables are both still referencing an actual, literal, concrete linked stack. And this is only valid because a linked stack is a stack, which is an object, and so on. So the type of the actual object is important. Yeah, okay. So there's an idea of binding. Look at this code. Look at this code and answer the question, given the above code, which version of toString would be called? I kind of spoiled this for you before. Assume you have some random number. Which version is going to be called? Array stack or link stack? Well, you don't know. You don't know before runtime. Before this code runs, at compile time, before I ever hit run, there's no way for you to know what version is going to get called. Is it going to be the version written in the linked stack or the array stack? We don't know. We won't actually know until runtime, until it gets there, until we know what the random number is. If the random number is less than 50, it's going to use the array stacks. If it's greater than 50, it's going to use the linked stack. Fine. But we won't know until runtime. So there's some code that we can know everything about it at compile time, but there's going to be some code where there's a bit of a mystery and we won't know until runtime. So connecting a call of a method to the actual implementation is called binding. Both because, now I said toString print, I guess the pushes could have been the question here too, but look at this code. It's a stack. Both the linked stack and the array stack are stacks. And a stack, we can push. We can push things onto a stack. So Java is happy looking at this code because it's like, well, they're stacks, and if they're stacks, I can push. So I'm going to call the method push. But it doesn't actually know which version of push it's going to run until runtime. So this is what I mean by the call of the method. Java knows, because they're stacks, that we can call push. Java doesn't know which version is going to be actually run, which actual implementation. Sometimes this stuff is known at compile time, and this is called static binding, where if I said, like, if after this line of code I said myStack.push, well, static binding, it's going to be the array stacks version because it's an array stack. We know that. But sometimes it doesn't, we don't know until runtime, and that's called dynamic binding. And by the way, it is possible to get the specific class at runtime. You can query it. Every object has a method called getClass that just returns its class. That we inherit from the object class. But FYI. Polymorphism. It's the idea that the behavior of the object is dependent on the type of the object, not the type of the reference variable. People get weirded out by this, but to me this is the most intuitive thing that we have. Like, no. To me, I find this to be remarkably intuitive. If you're having a hard time with it, I think you're overthinking it. When you tell an object to do something, the object is going to do the thing based on what it is, not based on what the reference variable is. That said, I wouldn't be able to say, in this example right there, those two lines there, I would never be able to say O.push. Because Java is going to be like, that's an object. I don't know if objects have a push method. In fact, I can guarantee you objects don't have a push method. Maybe a specific type of an object has a push method. But a reference variable of type O, I can't call push on it. You would then say, well, yeah, but the actual type that it's referencing is a linked stack. But Java doesn't know that. Java only knows like what the reference variable is. You, as the programmer, can cast it, like we did in all the equals methods, where we take this thing of object and cast it to the proper type. That's the programmer saying, like, trust me, I know, trust me, it's going to be a stack. But I can't say something of type O, push. I can't do that. I can say my stack.push, because the reference variable stack, it's a stack. I know I can push. But the actual implementation, the actual code that's going to run, depends on the specific type. Is all this clear? It all depends on what the reference variable is, what the reference variable knows it's allowed to do, and the type of the actual object matters versus the type of the reference variable matters. Cool? Okay, any last questions about inheritance? We could go into a lot more detail on inheritance, but I'm not gonna. But I'm gonna recommend you go through this aside I have here. I'm not gonna go through it right now. But there is a classic example that people will teach in inheritance. I'm using this in my example. I say a circle or a square and a rectangle, but you can find a Wikipedia article about like the circle ellipse, square, rectangle, circle, ellipse. It's the same. It's the same issue, and it's funny. It's actually kind of a bit of a joke because it's a classic example that people will use to teach inheritance, but it's also hilarious. It's actually like it is such a sorry. This joke does not matter, but it's also such a cliche example of such a terrible example of inheritance. So everyone uses it as an example of inheritance, while it's also an amazing example of why you shouldn't use inheritance. So, and I kind of work through it, right? I explain why. The idea is, well, we can make a rectangle class, but a square is a special type of rectangle. So we can make a rectangle class and then inherit from it to make a square. But that's terrible. It's absolutely terrible. Don't do that. One of the safest ways to make sure you're not messing up with inheritance is if you don't use inheritance on concrete classes. You can use them on interfaces nice and fine, but as soon as you have a concrete class, that's when things can go bad. Just as like a rule of thumb type thing. Okay, any questions? All right, a bag. So we talked about what a bag is. In fact, we didn't really talk about what a bag is. We talked about two specific types of bags, an indexed bag and a sorted bag. They're both bags, and we had a bag interface defined, but then we wrote two specialized interfaces, the sorted bag interface and the indexed bag interface, but they extended the bag. So both are bags, and everything a bag can do, a sorted bag and an indexed bag can do, but they also have their own functionality, specialized for what they are. So we talked about the interfaces, but let's actually go and implement them. Now we're not actually going to implement like the base interface. We're not going to implement a bag. We're going to implement only a sorted bag and an indexed bag. And we'll do array implementations. This is entirely arbitrary. We could do linked implementations. It's fine, but I'm going to do an array implementation because. So if we've got an array implementation of a bag, it's going to be the same general idea as a stack and a queue. But unlike the queue, Remember how the queue, we used that circular array? It wasn't really a circle, but we pretended it was, where it would loop back. We're not going to use that here because, well, you'll see, actually, we'll see. Well, okay. The reason we're not going to do that is because with a bag, or with a queue, removing was always from the beginning, right? So it was always about like not having to remove the thing at the beginning and move everything down one. But with a bag, in general, we could be removing from any index, not always the beginning. So it doesn't really matter that the beginning is always is being updated in a clever way. This will be clear as we work through the example, and I want you to actually think about why it doesn't matter so much as we go through it. So yeah, unlike a queue, the front will always be index 0 for the bag implementations with the array. With bags, adding and removing can happen anywhere. Adding in the middle would require linear time operation to make room. Removing from the middle require linear time operation to make room, no matter what, right? So it's not like think of the queue. I don't know why I'm having a hard time explaining this right now. Think of the queue. No matter what, when I remove from the beginning, I got to move everything down, right? If we had the bad implementation of a queue. But so we got clever and just updated where the front was, right? But the problem is, when we're removing from a bag, we're not always going to be removing from the beginning. In fact, we're going to be just as likely to remove from anywhere in the bag. So if I remove from the middle, I got to close that gap, right? No matter what, I got to close that gap. And otherwise, my bookkeeping is going to become entirely unmanageable about keeping track of where the gaps are. We got to close that gap no matter what. The value of keeping track of the front and moving it down was only because the removed were always from the beginning. But because we can remove from anywhere, we got to close that gap. So we're stuck with a linear time operation on a remove. And similarly with an insert. We're not always adding at one end. We're adding at any arbitrary point. Whether it's an indexed bag or a sorted bag, where the thing gets added to the bag in the array could be anywhere. It's not always at one end. So we're going to have to make room, move everything down one, and then put the thing in. Remove something, you take it out, move everything back. So our add and removes seemingly seem like they're going to be linear no matter what. We can't take advantage of like the one end and the other end situation. Remove from the middle. Okay, an expand capacity will be required, but the simpler version, we don't need that fancy version we used for the circular array where we moved things around. This is just going to be a more basic expand capacity like we've done before. And the functionality of a bag, regardless of what specific version is, requires these things. So whether we're making an indexed bag or a sorted bag, we need these methods. Add, remove, contains, count, is empty, size, and iterator. So if we want to make an array indexed bag, in addition to these methods, we must also implement an add where we get to specify the index, remove where we specify the index, set, get, and index of. We could add more methods if we wanted. We could even do less if we wanted, whatever, but these are what we're going to do. For brevity, I'm not going to go into detail on all of these methods. We're not going to look at code for all of these methods. We're only going to cover some of them. I strongly encourage you to actually look at the code for the array index bag and look at all the methods yourself and see how they work. But we're only going to cover a couple of them here. Do we have any questions before we start looking at some code? All right. So an array index bag, what's it going to look like? Well, public class array index bag, type T, it's generic, implements indexed bag. Now, because it implements indexed bag, it also extends a bag, but we didn't have to include that here because that's just included in the indexed bag interface. So We're implementing the indexed bag. It's generic. I'm going to have two constants. It's always nice to have named constants instead of some arbitrary magic value sitting in your code. So a default capacity of a size 100. If you're wondering why 100, because a not found special variable, -1. This would be like if we're doing a index of. If we don't find what we're looking for, we return that sentinel value -1. But a value of -1, although almost all programmers would know -1, oh, that's a sentinel value in this context. It's better to have a name for it, so we give it the constant not found. Sure, its value is -1, but it's what we're using. And then we have an array of type T, we're going to call it the bag, and an integer to keep track of the rear. We don't need an integer to keep track of the front because the front is always going to be at index 0. Rear, well, that's going to change depending on how many things are in the bag. We're going to have two constructors. A constructor that takes some specified capacity, that's the second constructor. We make a new object array of that size, immediately cast it to an array of type T, and then set rear to 0. Perfect. So all the constructor is doing is creating an empty array of some specified size, and if it's empty, well, the rear is 0. And then there's the other constructor which just chains to this constructor by passing it the value for the initial capacity of whatever the default capacity is. This is the same as the array queue, the array stack, the country catalog, the course list, the friends list that we've done. That's all. So any questions about this? Okay, so we've got our constructors down, we have our fields. So now we need to start implementing these methods. Add, remove, contains, count, is empty, size. Iterator, which we'll talk more a little bit that later. Another add, remove, set, get, index of. And we're probably going to want our like toString equals and so on as well. Oh, you can't actually see it here, but we're going to talk about iterators later. So I'm going to create a couple of private methods here. Shift left, shift right. And the motivation for having these methods, I don't need these methods. I could include this code wherever I need it. But I always like using, this is going to be used enough that I think having a method for it's good. And it's also nice to have a name for a chunk of code. Shift left and shift right. Imagine I have an array with some arbitrary number of things in it. All right? And I want to add something to the middle. And I need to move everything down to the right. I got to move everything to make room for it. Although I don't need to move everything. If I've got 100 things and I want to put something at index 50, I only need to move everything from index 50 to the end down 1. Right? Because everything here is fine. I just want to like insert that thing at index 50. So everything needs to move down from the point I want to insert at. Everything needs to move down a little bit, 1 index, so I can put the thing in. That's what shift right is going to do. And shift left is the same idea, but the opposite. If I want to remove something at index 50, I want to move everything down 1. Right? Up to and including that index, but I don't need to actually anything after that. Or before that, I guess, from 0 to 49. Is that clear? So I'm going to have these as methods because I don't know, I think it makes the code a little nicer to have these as method as opposed to including these in the add and removes and whatnot. So shift left, what am I going to do? Well, I specify some starting index. So let's do shift right first. This is making room for adding something. I specify the index. It's called start, which perhaps isn't the right word. But I'm using a for loop that actually counts down. I start at the end, right? I start all the way at the rear. And then I say, okay, bag at index I is whatever is big at index I minus 1. So if I is 100, all right, first of all, remember, rear, we're going to follow the same pattern we did every time we used an array container before, where rear isn't really the rear. Rear is the next empty spot, right? So if I start at rear, if I have 100 things in my array, indices 0 through 99 are filled. I want to insert something at index 50, some arbitrary index, I just picked 50. So I go to index 100, okay, which is actually empty. And then I go to, so I is 100 right now. What's 100 minus 1? 99. So you go to index 99, you copy that there. And then I decrease, you'll see in that for loop, I decrease, I minus minus, I go to 99. I take the thing at 99 minus 1 and move it to 99. Go to the thing at 98 minus 1 and move it to 98. And I do that all the way down to that index where I actually want to insert something. Cool? It's just a nice helper method to make room for stuff. And then the other one, shift left, well, it's the same idea, but if I'm closing the gap, I start at the index I want to get rid of, or I want to like close the gap on, and go to the next index, move it down 1. Go to the next index, move it down 1. But notice that that loop actually goes to rear minus 1. It's actually less than rear minus 1. So imagine, for a second, I have an array with 100 things in it. Indices 0 through 99 are filled. Rear is 100 though. Rear minus 1 is 99, right? But I go, I is up to but excluding 99. I will never get to 99. I will only ever get to 98. Is that clear? I hope this is clear, but if not, I'll say it again. I have 100 things. That means indices 0 through 99 have things in it. One thing's being like obliterated by being shifted down, but that's not important right now. This loop is going to go from I to rear minus 1. Rear minus 1, well, that's 100 minus 1. That's 99. Which makes sense because it's the last thing. But we're not actually, I will never get to 99 though, right? Well, hold on there. I will never get to 99 because it goes, I is less than rear minus 1. Right? But look at what's happening in the loop. I go from index I, so I'm at index, I is 98 right now, okay? What does the code say in the loop on line 49? Bag at index 99, you're going to be bag at index 99, no. Bag at index 98. What's 98 plus 1? 99. So then I can actually copy the thing from 99 to 98. If we ever had, it would be an edge case where it just so happened that the array was full. We've got to get an array index out of bounds issue here. Let me put it this way. The way it's written here. But if you didn't have that, you could say like, well, it would still work unless it was already at capacity. I'm trying to think of another example. If I have, raise your hand if this was clear to you and I'm beating a dead horse. Really high, I want to see. Okay, so half of you don't think I'm beating a dead horse though, so it's still alive. If I had a loop and I wanted to always add adjacent pairs of elements in the array. Okay? Well, I could go through an example, but I'm struggling because I feel like, okay, raise your hand if the reason you didn't raise your hand before was because you weren't paying attention. Okay, so that covers about half of them. All right, I'm just going to move on then in that case. And I'm just going to assume this is clear. Because we go to I plus 1, we could have an array index out of bounds issue here, right? I never want I to get to 99, because if it ever got to 99, it would want to go to index 99 plus 1, which was 100. There's nothing at index 100 if there's 100 things in the list, though, in the array. Only 0 through 99 are full. So that's why we want to go up to and excluding rear minus 1, because we do the rear plus 1 inside the loop. That's all I'm saying. This is a beautiful example of one of the 2 hard problems in programming. Who remembers what the 2 hard problems in programming are? Caching, which we're not going to worry about. Naming variables, really hard. And of course, off by 1 issues. So this is an example. It's a joke. Oh. Off by 1 issues, but this is an example of an off by 1 issue, right? If you don't get the joke, now I'm really, what's going on today? Holy moly. The joke was, I said there are 2 hard problems, but I said that I explained 3 problems. But the last of the third of the hard problems is an off by 1 error, which is the joke. Okay. Come on, it's funnier than that. Just give me a break. So shift left and shift right, they either make room or close a gap in the array. If we want to add something, we might need to make room. If we want to delete something, we want to close a gap. Iterator methods, they're going to be the focus of another topic, but this is what they would look like. Public iterator of type T. So this is a method that returns an iterator. The name of the method is iterator. And it's just going to return a new array iterator. That's all we'll talk about iterators for right now. But all it does is make an instance of an array iterator and return it. Add methods. Well, I've got 2 versions here. And one just delegates the responsibility to another one. So the general add, the add that we get from the bag, where we don't specify an index, that's going to be append. All right? If I ever add something to my bag, but I don't specify an index of where I want it to go, it gets added to the end. I'm also going to implement another add where I specify the index where I want the thing to go. You will see that specifying the index is a more general version of the appending to the end. Appending to the end is just always specifying the last index, like the rear. So the general, or not general, it's not, the add that we inherited from the bag class just calls the more specific add, but we specify the rear as the index that we actually want to add the thing at. Cool? Yeah. Otherwise, we specify the index, and I've got to check here. If the index is less than 0, or the index is greater than size, not greater than or equal to size, though. If that happens, we're going to throw a new index out of bounds exception. If you try to index an array at index -1, that's what you get. So we're just going to use an existing exception type and use that because, well, that's exactly what's going to happen. Index out of bounds exception. We're trying to index a bag at an index that doesn't exist. Now, there's 2 parts of this, the less than 0. Hopefully that's pretty obvious. there is no index less than 0 for an array. So if you try to specify an index that's less than 0, that ain't going to work. Raise the exception. Now, you might think to yourself, shouldn't index be greater than or equal to size to raise the exception? Well, I know if you're thinking, well, hold on, if I have an array of size 10, right? There is nothing at index 10, right? But remember, I can say add to index 10. It's the next spot. It would become the 10th thing. So that's that edge case where we actually want to allow to add at that last index because that's equivalent to an append. Cool? Now, if you specified size was 11, well, okay, yeah, no, that's no good. But when we're adding something, we're specifying the index where we want it to end up. In index 10, if there's 10 things in that array, 0 through 9 are filled, I can also specify I want to add it to index 10. There'll be 11 things in the array now, but the new thing is added at the end, which was index 10. Cool? So that was just that funny little edge case. Okay. So this is the exception check. Now here, this is my expand capacity. If we are ever trying to add something, I don't care where I'm trying to add it, the index where I want it to go is irrelevant. If there's no room left in the array, we're out of room with our array. If I have an array of size 10, and there are 10 things in that array, and I want to add it to index 0, 1, 7, it doesn't matter, there's no room. Right? You agree with that statement? We need to then expand capacity. Now, every time before when we did expand capacity, we wrote our own private method expand capacity, right? Well, the good news is there's actually like a built-in one of those, and we'll just use it now instead of writing our own. And it's in the arrays class. It's full of a bunch of static methods, so like functions for arrays. Arrays copy of, we specify what array we want to make a copy of, and then we specify how big we want the new array to be. So bag.length times 2. There. So now this is just an easier way to do expand capacity. In general, going forward, this is what you should be using. The only reason I made you write the expand capacity before was, well, you got to learn how these things work, right? So you did it, you learn it, you understand it. Well, now you use an existing one. Yeah?
So could you use that for like an array stack?
Yeah, you could. Yep, you absolutely could. Now, if I said on the exam, like, write an expand capacity method, and you do that, I'm going to be pissed. But in practice, use this, okay? There's another one. There's like a system.array copy or something like that. I can't remember what it is. There's nothing, you could use that one, but that one's actually like less nice. This one here is a nice pure function. The other one has side effects and it modifies the values of the arguments, or at least it modifies the values of the things that the arguments reference, which its side effects not great. This is a little nicer, it's a little cleaner. So I recommend this one. But in order to use it, you would need to import arrays, but whatever, no big deal. So we've covered you specified an index that's not valid, we throw the exception. If we're out of room, we need to expand capacity. If we're not out of room, you skip this, it doesn't matter. Otherwise, what do? Well, we shift right, we make room. So shift everything right, starting at that index. Or at least not starting at that index, but I want room to exist at some specified index, index 50. So everything's got to move down one. Bag at index is the element. We increment rear, return true. There. That's all. By the way, if we go back here, you'll notice this, where I set the thing at the index to be null, or I set the thing at the end to be null. Not necessary, but this is my philosophy of if it's not supposed to be there, get rid of it. Even though it doesn't really matter functionally, it would get overwritten immediately. Still, if it's not supposed to be there, get rid of it. Cool. But back to the add. And you know, I think this is an example of, like, look, we're writing an add for a collection, a bag, an index bag. That's a fairly general purpose data structure, like a list. That means it's actually pretty complex. It's pretty sophisticated. In adding something to a data structure, data structures are stateful. These things are hard to test. It's going to be, I mean, it's one of the heavy lifting methods for this data structure. It's a big deal method. But I feel as if, like, this is pretty bite-sized for you. Because we've been emphasizing coding well and whatnot. Like, look, the code is self-explanatory. If it's the wrong index, raise the exception. If we're out of room, make room. Otherwise, shift to the right, add the thing at the index, increment the rear, return true. Right? We've been very careful to create the code in a way where the code ends up being kind of like elegant. Right? Yeah? I think it's nice, right? We could implement this thing in a lot hairier kind of way, which I don't recommend. But in the end, you know, and also, like, by making use of other functions, like, the shifting to the right is kind of like the most complex part of the add, I guess. But, you know, we wrote a method to do that. And we just now call it. Oh, it's so nice now without it. Yeah, cool. Any questions about the add? Yes?
Just going back to the shift left.
Shift left, yes.
Do we not have to adjust what the rear value is for that?
So, what do I say? Shift elements to down left, and the starting index specified. So, you raise an interesting question. So, if no one heard, the question was, well, when you're shifting to the left, where the rear is being changed, right? So why didn't I update it there? Well, I mean, same thing for shift to the right. When I make room, the rear is actually in a different spot now. I could have put that into here. But the reason, now this was purely a design decision, okay? So I could have updated the rear in these methods. Okay? I could have. Or I could have done it the way I did it, where I leave the rear alone. But to me, in my mind, I was like, shifting to the left and shifting to the right, they have one job. You move everything down one in an array. You move everything to the right in the array. It's got a side effect. This method it's side effect written all over it. It's got no return value, and it's modifying the contents of the bag. It's changing the state of something. So it's already got side effects. That's not why I'm not updating the rear there. It's full of side effects. But to me, the purpose of this method was to move things up or down in an array. The purpose of an add is to add the thing and do all the necessary updating. There would be, if you were to implement it such that it did do that for you, fine, then you wouldn't have to do it here. But to me, for the consistency with the other data structures we've written, where we always incremented add, like the rear and the add, and keeping that method, the shift left and shift right, to be very single purpose, that's why I decided to design it that way. But you are absolutely right. It's not necessarily better or worse. All I can do is explain why I implemented it this way, what my motivation was. And as long as there's method to the madness, you're usually pretty good. Very good observation. Did anyone else notice that or think about it, or no?
I thought about it and I just do it right.
You thought about it and was like, oh, whatever. All right.
Maybe use it at some
Now remove. So I've got two removes. Let's start by looking at this remove, where I remove something from a specified index. When you remove something from a specified index, that's the remove from the indexed bag. So if the index I get is not valid, I raise an exception. Okay? But here you'll notice I actually say if index is greater than or equal to size. Right? Well, because now, before, I could add something to the index that didn't really exist yet, because it was available, really. But now if I say remove something at that index, well, that's not valid. So that's why the edge case has changed a little bit here to be greater than or equal to size. Because if I have indices 0 through 9 are filled, but rear is 10, and I specify 10, well, it better not work. I can't remove something from index 10. Otherwise, what do? I get the element at the specified index, I shift left, decrease rear, return the element. So go to the index I want the thing from, remember it, move everything down to close that gap, update where the rear is, decrease it by 1, and then we return the element that we wanted to return. Yeah? So far, so yeah, we're happy? And then there's the remove where you specify the element. Here I don't specify the index, I specify the element. Well, here I'm kind of just cheating, and I'm doing a lot of delegating. I'm calling this contains method, which we haven't looked at yet, but it's just basically a linear search that returns true if the element exists and false otherwise. If the element is not contained, return false. It's not there. You can't return anything. Well, you can return, there's nothing to remove. It failed. Return false. Otherwise, find the index that we want to remove from by calling this index of method. And then just delegate to the other one where I say remove from the specified index. That's all. And then return true because it succeeded. You might wonder, well, hold on. This remove returns something of type T, which we see there. This remove returns a Boolean. So, we're returning true. Okay. But when I call this remove, the one where I specify the index, that's the one that returns the value. And I'm not doing anything with the return value. It's because I don't need to. It's just remove it. Doesn't matter. Yeah?
For like the bottom one where it has like key element, if it were like integers, how would it know like which one to do? Because the one above is like integers.
Good question. Yep, you'll have an issue in the case where those are the same. Here's this question. Actually, there's a lot I want to unpack here, but I'm going to answer your question, and hopefully I can remember on Friday what else I wanted to talk about. What happens if you have your generic type that you've got an indexed bag of is integers, right? And you said remove 5. What's Java going to do? Is it going to call the one where you specified the index, or is it going to call the one where you specify the value of the element? Right? What are you going to do? Well, in that case, yeah, Java would have a problem. And you run into an ambiguity issue. There is a solution, however, though, because you might say, well, the types are the same. They're not. Because you can't have generics of primitive types. I can never have an index bag of ints. I can have an index bag of integers. Now, 99 times out of 100, if you put an integer in, like an int in there, it's integer. Java's fine with that. But on the off chance that you have a potential ambiguity, you can resolve it by saying like integer 5. But you have to go out of your way to specify. And in fact, if you go and you look at the unit tests for the indexed bag, I think it's the indexed bag, you will actually see examples of me doing exactly that because it does create ambiguity. Very good question. Very good question. You should be really proud of yourself for that one. Now, the other thing I wanted to hit while we have a moment is, well, we have removes with two different types being removed, like the return types. That's kind of weird, right? Well, the general purpose remove if I specify an element that I want to remove, what's the point in getting a reference to the element that I already have a reference to of the same value as the return thing, right? Like the general purpose remove for any Java collection is a Boolean, right? If I say remove the string hello from a list of strings, I know I had, like, the argument was the string hello, and it's going to return a reference to the string hello. Okay. Or return a Boolean. True, it succeeded. Where the other one, if I say remove the thing at index 7, well, that might be the string at hello, the string hello, and I actually might want the value that was actually there. If you're saying, well, but why'd you do it that way? Honestly, it's kind of arbitrary. There was a design decision to do that way, but if you're thinking like, what's mathematically making sense here, that's whatever. But we'll pick up here on Friday.